Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll solve a problem on reaction radial flow turbine. So the question here I have taken, a reaction turbine works at 450 rpm under a head of 120 meters. Its diameter at the inlet condition is 120 centimeter and the flow area is 0.4 meter square. The angle made by absolute and relative velocities at inlet condition are 20 degree and 60 degree respectively with the tangential velocity. Determine the volume flow rate, power developed and the hydraulic efficiency, and assume that the wheel at outlet to be 0. So for this problem it is given a reaction turbine. Okay, so for this problem the diagram I have taken here, this is the blade and this is the impact of jet at the inlet condition, and this is the component of the velocity, horizontal and vertical, and this is the outlet condition is there, outlet velocity triangle here. So outlet wheel velocity at outlet condition 0 means it will be 90 degree here. So what are the data are given in this question? Let's write down this, then we'll go for the answer. So the solution we can write, what are the first, we'll say what are the data are given in this question. So first thing, if you see that in the first line itself, the turbine is speed is given. That means n is given 450 rpm. Speed n equal to 450 rpm under a head. So h is given 120 meter. In the first line itself. Now next one is the diameter of the inlet condition is given. So I'll take it. This is diameter d1. D1 is given 120 centimeter. So we can write in terms of meter, that is 1.2 meter. So what will be the flow area? Flow area is already given. This is pi. We know that flow area is pi d1 b1. This is equal to 0.4 meter square. This one actually I have told you in the last video lecture how we used to consider the area of this. So now the next one is the angle made by the absolute velocity at inlet condition. So that is nothing but we can write this is alpha. Alpha is 20 degree. So this is the absolute velocity which makes an angle at the inlet condition. So how much? This is alpha, and similarly theta is this one, absolute velocity at the inlet condition, theta, this one with respect to this. So alpha is given 20 degree and theta is given here 60 degree respectively with the tangential velocity. So tangential velocity is nothing but this one, or we can say this velocity. Okay. Now wheel velocity at the outlet condition, assume that the wheel at outlet to be 0 in the sense we can write this is VW2 is 0 here. So exactly previously what used to happen, this used to there and this is the value of VW2. Now this VW2 is not there because it is given radial, or assume to be the outlet to be wheel velocity is 0. That means VW2 is 0. That's why we have not given anything. Directly you can do a right angle triangle here. So for that we need to find out volume flow rate, power developed and hydraulic efficiency. So first we will do one by one terminology to find out this volume flow rate, power and hydraulic efficiency. So at the starting I'll first find out the tangential velocity. So tangential velocity formula, we know that u1 equal to pi d1n by 60. So here we can write this is pi, this is 1.2 and this is n is 450. 450 divided by 60 is there. Now this one we need to calculate with the help of calculator here. So pi into this is 1.2 and this is 450 exact divided by 60. We'll get 28.27. This is we got here 28.27 meter per second. So this one I have calculated for the inlet condition tangential velocity. So the inlet velocity flow, if you see this one, this triangle. Okay. Now here from this triangle, what I can write here, suppose let me consider the formula of tan alpha. On behalf of sin alpha, cos alpha, I'll go for directly tan alpha. So tan alpha I can represent in terms of like flow velocity, this one, and with respect to the base. So this is VW1. So I know the alpha value, that is 20 degree equal to, we can write this is VF1 by VW1. So VF1 you can write because these values are not given, but I need these values for the future calculation actually. That's why I'm writing directly here. And this one again, I can write VF1 equal to, I can write some 10, 20 value we can calculate. This is 20 and go for this 0.006. So here we can write this value. Let me check it once. That much small will be not there. 20. This is, yeah, this one. Double I have clicked. 0.363. So I can write here. This is 0.363 point something is there. We can write this much VW1. Okay. This is for at inlet condition. Similarly, at the inlet condition, one more terminology I can write in terms of theta. Okay, because these values are not given. So how I will find out these values of VF1, VW1 in this method? So again, I'll write here. This is 10 theta. So 10 theta, what I can write again, this perpendicular I can write here. So that is VF1 with respect to this value I need to write. This is how much? We don't know this value. So we can write VW1 minus E1. So here I'll write this is VW1 minus E1. So 10 theta value is given 1060 degree minus VF1. So VF1 value I'll write this value here. So this is 0.364. This is VW1 with respect to like denominator VW1 is there minus E1 value is given. Yeah, we have calculated already. This is 28.27 meter per second. Now, what is the value of 1060? Let's find out this. 60 with respect to that 1060 is nothing but 1.732. So I can write in this way 1.732 is equal to, here we can write this value like 0.364. So otherwise I'll do one thing, I'll take this value to other side. It will be completed here. So this one directly I'm writing here. This is VW1 minus 28.27 equal to, this is 0.364 VW1. So I'll take now VW1 one side, I can take it, and the remaining value I can keep it to other side. So let's multiply first. So this is 1.3732 minus this value. This is 364 bracket close. This much VW1 equal to, this minus term will be this side. Again, if I take it to the right side, then it will be plus. So what I'll do, yeah, multiply 28.27, 48.96. So this is 48.96. Now here I can find out the value of VW1. So VW1 equal to, this one I can write 48.97 divided by this terminology. How much we'll get here? Very, very less. So directly I'll write divided by bracket start 1.732 minus 0.364 bracket close 1.368. Yeah, this is 1.368, and finally how much we got? 35.79. So this one I can write, this is 35.79 meter per second VW1. Now I can find out the value of VF1 because already we got this equation here, VF1. So VF1 equal to, you can write this is 0.364 into 35.79. This one equal to, we can write this multiply 0.364, 13.027. So this is 13.027 meter per second. These are the data, basic data we require to calculate for volume flow rate, work done, power developed, hydraulic efficiency. So let's find out one by one now. The first one is volume flow rate. So volume flow rate, how we can calculate? Q equal to, we can write this is pi d1 V1 area into VF1. Okay, so this value already given in the question, that is nothing but 0.4 into VF1. Just now we have calculated 13.027. So we'll get some 0.4 means half of this, again half reduce also. This is multiply 0.4, 5.21. So this much volume flow rate, 5.21 meter cube per second. This is the first answer we found now. The second one, again, just go for the, before calculating the power developed, we need to calculate the work done. So I'll write the work done per second on the turbine. That equation, we know that this is actually rho Q VW1 E1 plus VW2 U2, plus minus actually there, but this term is 0. So only you can write this is this terminology. So rho value is 1000, Q value is, we have calculated just now, 5.21 into bracket start VW1. What about the VW1 value? Yeah, 35.79. 35.79 into this is 28.27. We'll get work done. And if with respect to power, if you want to calculate, we can write this power is nothing but the work done per second, what we got here, divided by 1000. So that much kilowatt will get. So anyway, I'll just write this value, multiply 1000, multiply 35 point, this is 79, again multiply 28.27. We got 5272,896. 52 here, 5272,896 something we got here, this much Newton meter per second. So how much we got here? Just to put the value here. So same thing I can write in this value here, and finally I can write this is 5272.896, this much kilowatt power. The last one is efficiency. So hydraulic efficiency, what is the formula of hydraulic efficiency? We know that this is VW1 E1 by GH. VW1 E1 by GH. So VW1 equal to 35.79. We have already calculated. This is 28.27 divided by GH. This is 9.81 into H. This is 120. That's it. We can find out the value of hydraulic efficiency. So let's do it. 35.79 into 28.27 divided by bracket start 9.81 into 120 bracket close, 0.859. So 0.8594 we got here. Now this one we can convert into percentage, that is nothing but 85.94 percentage. This is our last answer for the efficiency, hydraulic efficiency. This one, the first one, we got volume flow rate. Now we got this power, this much power developed, and this is our hydraulic efficiency. I hope you understand this problem, how to solve it. Simple, only you need to remember this, some formulas are there. If you are having any kind of doubt and query regarding this, you can give a comment in the comment box.